Good evening. Welcome to the Fall 2009 final presentations for OU's Center for the Creation of Economic Wealth. I'm Daniel Pullen, and I have the great opportunity to serve the university as our Vice President for Strategic Planning and Technology Development. And as part of our technology development efforts, we have, starting in 2006, created this incredible mechanism for growing and diversifying Oklahoma's economy called I-CCEW. In our 3 years, we've welcomed 101 very talented interns from across the entire university, both grads and undergrads from 9 different colleges and many more majors. And this diversity has really, I think, borne itself out with some tremendous commercial success. In fact, the program has become quite competitive, and so we'll get to know our incoming interns toward the end of the evening, but you can rest assured that you are in a very select group, because actually the past 2 semesters we've had over 4 times the number of applications as we do have internship slots. And those that are applying are no slouches. I think the program has developed a reputation for student excellence, and we're just so proud to keep attracting these great, diverse young minds. So again, welcome, and selection is very special. We're proud to have you. Before we get going tonight, though, I do want to recognize a few folks who have been highly supportive of the program, who actually are allowing us to provide scholarships for each of our interns, and that includes Regent Tom Clark, Ron and Joan Yagoda, and our first corporate sponsor, Beyond Petroleum, or BP. So please join me in recognizing our sponsors. So while we've only been in operation for about 3 years, the idea for CCW is not necessarily new. It's something that was bandied about at the turn of this century by 3 really amazing folks. First, President David Boren. Second, Gene Rainbolt, the chairman of Bank First. And then finally, Dr. Skip Porter, the retired vice president for technology development and former dean of the College of Engineering. These 3 intellectuals really thought long and hard about the role the university should play in boosting Oklahoma's economy, and how is the university uniquely positioned to achieve these gains. And we really owe these 3 gentlemen an intellectual debt. So again, let's recognize our intellectual forefathers. Okay, so I see a lot of friendly faces, but a lot of new faces as well. So I'm just going to take a quick moment to talk about CCW, how it's structured, what do we do here, and so on and so forth. So essentially, we commercialize Oklahoma-based technologies by engaging inventors, mentors, and talented students to create wealth for Oklahoma and the nation. And I think it really encapsulates the university's unique position as a catalyst for economic growth and diversification. Because what we do is we bring together 3 assets that are very unique to a university. We bring together our faculty, we bring together our alumni, and as well as our talented students. And it's really that mixture coming together, working on challenging problems, that positions the university in just such a fabulous way to be effective in commercializing technology for the whole state's benefit. Like any business, you need an idea, you need a strategy behind that idea, and ultimately you need to be able to execute that idea. And with sort of that framework, that's actually how we've designed CCW. So an idea comes from our talented faculty. You know, they're in the labs on a daily basis, generating intellectual property, and that's sort of the kernel of value around which we then put some structure around from a strategic perspective. And that's when we bring in our alumni and friends of the university to serve as mentors, who can engage the faculty and say, okay, well, you know, in my business experience, you might go this way, or, you know, you don't want to go down that path because it's fraught with risk. And so we can add the strategic element to it. And then finally, from an execution perspective, we've got all these talented students who want real-world entrepreneurial experiences, who want to differentiate themselves vis-a-vis their peers through true business experience and understanding, such that when they're out trying to get into the top grad schools, or they're trying to land that coveted job, they have a story that's differentiated, something more to say than maybe the average student. And so they're very, very willing to partner with our alumni and our faculty, again, in this unique way to move technology forward. I think there are 2 returns on investment for our program. Obviously, in the short term, we want to commercialize technology. And I think that we have a nice track record of doing that. In fact, we've looked at about 15 opportunities in our 3 years. That's resulted in 4 different licensing agreements from the university to the private sector. Our students have helped spin out 2 new companies from scratch, and along the way, they've managed to pull in about $4 million to support technology commercialization in Oklahoma, all due to our students and our alumni and our faculty all working together. That's why the university is so uniquely positioned to contribute to Oklahoma's economy, and we're very proud of that. But that's just one return. The long-term return, I think, and maybe even more importantly, is where these young faces go. I think what we're really doing is cultivating the next generation of entrepreneurial leadership for our nation. It's what we have. We're creative, and we work hard, and we're entrepreneurial. And that's been the hallmark of this nation. And I think that many of our most talented students that are coming through this program are recognizing that and wanting to be a part of that in the future. And so when I hear that our students are going to MIT and Oxford and Harvard Business School, and they're going to Goldman Sachs and ConocoPhillips and really great companies, it excites me because I know they're going out and acquiring the best practices that hopefully they're going to bring back to Oklahoma in a leadership capacity to pay it forward and ensure that the competitive longevity of our state and nation is secure. That's the real long-term return on investment we're talking about here, and that's maybe what excites me the most. So again, I can't talk enough about the program, but I think what's really important is talk a little bit more about our students and staff and why we're all here tonight. So I want to turn it over to Mariana Barrientos, who is the CCW program manager and who is actually a former CCW intern herself. She was a member of our very first CCW intern class in the fall of 2006 and just does a great job leading this program. So Mariana, please join me here.
Yeah, I think I have this. Thank you, Daniel. I have some technical problems here. I am extremely proud to introduce 3 presentations that depict the dedication and clever work of 3 outstanding CCW teams this semester. Tonight, I represent CCW staff members. I can speak on behalf of all of us when I say that we feel twice as privileged for 2 reasons. On one hand, as Daniel mentioned, we have had the opportunity to be part of the evolution of the program from its early days, as we are all CCW alumni, except for Daniel, but representing the 1st, 3rd, 4th, and 5th CCW classes. But at the same time, we have been very fortunate to be part of the evolution of the 10th CCW class. From their graduation from boot camp at the beginning of the semester to tonight, to their becoming specialists in their particular fields of their projects. These students, however, are very outstanding. And before moving along, I would like to brag a little bit about them. Tonight, by design, CCW aims for a diverse source of talent. Tonight's students represent 4 continents and 4 countries across the world, including the United States, of course, Nigeria, England, and China. These students have an average GPA of 3.77. But what is really remarkable about this is that these students represent award-winning athletes, campus activists, outstanding sophomores, juniors, and seniors from 5 colleges and 10 majors across the university. We have letters, engineering, political science, business, as Daniel mentioned, a variety of sources of talent. But just as important as the diversity of these interns are the commonalities. And the first common denominator of these interns is their strong intellectual horsepower that has made them able to arrive to sound conclusions and recommendations based on thorough research and analysis throughout the semester. At the same time, these students are mature beyond their years, which has facilitated their successful interaction with top OU researchers and with industry leaders from Oklahoma and the nation. More important, however, these students are very intellectually curious and passionate about these technologies. And it's this passion and curiosity that has driven a very strong culture of work ethic. In virtue of this culture, these students have spent 15, 20, 25, or even more hours per week to make progress and overcome obstacles in their technology commercialization projects. And as you're about to see tonight, tangible progress to strengthen and diversify Oklahoma's economy has taken place within the walls of CCEW this semester. New walls, by the way, since we have moved to a very nice location in the research campus recently. However, these results wouldn't be possible without the other components of CCEW's secret sauce, which include the visionary minds of the inventors of these innovations, and also the experience of private sector mentors that have provided support and guidance to these students throughout the semester. Therefore, to introduce the first presentation of the night, I would like to welcome Mr. Christopher Mizell. Mr. Mizell is an attorney at Dow Loans, and he's also an adjunct faculty member at the OU College of Law, and he has several years of intellectual property practice experience. So please help me welcome Mr. Christopher Mizell.
As Mariana mentioned, I'm Chris Mizell. Good evening to you all. I have had the privilege of being the mentor to Team Garage Analytics. And what I would say, this is my first experience with the CCEW program, and it has been a great one. I will say that in terms of a university environment to provide this sort of thing to students is, frankly, is incredible. The idea that a group of highly talented, competitive people can come together, work on a project in a very compressed time frame, and essentially come out with, frankly, years of real business experience in a period of 12 or 13 weeks is a tremendous advantage, I think, both for the university and for the students to come through. From the first day, on a weekend when I came in and, we reviewed the project with these people, I got my team, we met, we had a brief meeting regarding the technology, and shortly thereafter, I mean, these people were on this thing like dogs on a bone. It was incredible. I mean, we stood in Stevenson, and I remember thinking, wow, I expected, there to be, a degree of curiosity and passion about it. But they were just on it, they were immediately engaged. I went home, to my wife who teaches here at the university that night, and I said, this defies every poor stereotype you hear about these kids today. That my saying, and I was very excited about it. They went through highs, they went through lows. We would meet, I would get emails at, 2:30 in the morning from, the team leader saying, can, we have a meeting tomorrow at, 9 a.m. I know this is short notice, could you come listen to this thing? Sure, I'm glad to do it. They were wonderful. I could sit here and blather on for, 10 or 15 minutes about how terrific they are and how much they applied, to their project. But I think, that is a truth that's going to be self-evident here momentarily when they come up and speak to you. So without further ado, I would introduce to you Team Garage Analytics.
Good evening. I'd like to thank you all for coming tonight and welcome you to the final presentation for Team Garage Analytics. My name is Buzz Becker. I'm a political science and economics junior from Tulsa, Oklahoma.
My name is Benjamin West. I'm an entrepreneurship and finance junior, and I'm from Rochester, Minnesota.
I'm TJ Moen, industrial engineering junior from Weatherford, Oklahoma.
I'm Taylor Krebs, a junior in economics and international studies from Albuquerque, New Mexico.
Our team inventor is Dr. Robert White, and he's an analytical chemistry professor here at OU. Our team mentor is Chris Mizell, who you just met, and he is here in Norman with us with Dow Loans Law Firm, and our team leader is Miss Brittany Ryan. I think all of us have experienced bottlenecks in the workplace. These exterior circumstances or constraints are very frustrating when they're the thing that's restricting us from getting our work done. And Dr. Robert White had a very similar experience in his own chemistry lab, and that's why we're here tonight. Luckily, he approached it with hard work, ingenuity, and resourcefulness, and came out with a very innovative technology that actually started in his garage, hence garage analytics. Before we delve too much in the technology, I want to outline or go through a quick roadmap for y'all so we have an outline for the evening. First, we're going to talk about the technology. We're going to talk about it in a broader sense so you understand what we're working with, and then get more specific to Dr. White's technology so you understand how much he really is shaking up what's currently out there. Then we're going to move on to the market, because as much as innovation is important, it's also important that we can make a buck on it. Then we're going to talk about development options. If there is this awesome technology and ample opportunity in the market, how do we get our technology to start competing? Then we're going to talk about a prototype. What are the companies we need to be seeking out in developing a prototype? What are the traits that are important in making a prototype? And what are the benefits in really advancing the technology that direction? We'll then finish up with some next steps. So let's talk about the technology. What we're dealing tonight is gas chromatography. For those of you who aren't familiar with that, what gas chromatography is the separation and analysis of chemicals and elements using heat as the catalyst for separation. It does this by vaporizing them without decomposing them. So kind of think of it as analytical chemistry's version of a centrifuge, except where a centrifuge obviously uses acceleration to separate, gas chromatography uses heat. And here's a rough skeletal outline of a gas chromatograph. What a lab chemist would do is inject a substance through the sample injector. As the substance goes into the oven starts to rise in temperature. Now, each element begins to separate from the substance based on their chemical affinity to the coil there in the oven as the temperature rises. Once it passes through the coil entirely, it goes through the detector where the gas chromatograph analyzes. A traditional gas chromatograph technology is about 13 liters in volume, and this is one of the big restraints on the technology. If 13 liters is hard to grasp, it's like a very large industrial microwave. So that's the big restraint, is heating up all that area to get the experiment flowing. And the traditional technology is heating up at about 0.5 degrees Celsius per second. So where does Dr. White come into this? Well, Dr. White saw that the critical restraint on the technology was that oven size and the speed that experiments take place in. So he scaled it down to about the size of a small tissue box. As you see here, Dr. White is able to attach his technology onto the traditional gas chromatograph technology, utilizing the sample injector therein on the technology and the detector, but enjoying the additional functionality of a much faster oven. So whereas previously, the volume of the oven was the biggest restraint in experiment time, and we were moving at about 0.5 degrees Celsius per second. At a much smaller volume of the oven, experiments are now moving at about 2.5 degrees Celsius per second, thanks to the coil being down to about a fifth of the original size. Now, when we first saw this, obviously, relatively, it's awesome. It's 5 times as fast. But does 2 degrees Celsius per second really make a big difference? Let's stack up Dr. White's technology versus the traditional and extrapolate it a little. Let's see if it really makes a difference. So a typical experiment is going to go up to about 300 degrees Celsius. Now, if the traditional technology is heating at 0.5 degrees Celsius and cooling at 0.5 degrees Celsius, that means that your average experiment is going to be about 20 minutes. So in a typical lab day that takes 8 hours, that translates to 24 experiments per day. And we're assuming utter efficiency in that lab. With Dr. White's technology, that same 300-degree experiment is heating at 2.5 degrees Celsius per second and actually cooling at 10 degrees Celsius per second. That means one experiment is only 3.2 minutes. Now there's an improvement. So that same 8-hour lab day with Dr. White's technology is no longer 24 experiments. Ladies and gentlemen, we're talking 150 experiments. That's not to say this technology is perfect. There are some things that need to be improved on down the road, which we will be addressing, but that speed is incredible. So, 3 traits we thought were most promising in Dr. White's technology. Obviously, the speed. In both university chemistry labs and professional ones, not having to worry so much about the experiment time when projecting a project timeline is a huge improvement over current technology. Also, the cost. The fact that Dr. White's technology can be produced at a fraction of what's out there on the market right now, and your decrease in production costs. Whether it be decrease in energy and actually heating up the oven, The liquid nitrogen used to cool gas chromatographs, obviously we're cooling a much smaller volume, so less liquid nitrogen is used. And then lab overhead costs us lab wages, so we're not wasting as much time. And then as we addressed earlier, the fact that Dr. White's technology is able to attach to traditional technology gives us a very, very exciting market entrance, but I'm going to let Ben talk more on that.
Thanks, Buzz. To really understand the value of the intellectual property, it's important that we understand both the size and the strength of the market in which it competes. Gas chromatography is a segment of a broader market known as the chemical separations instrumentation market, which was valued at $6.3 billion in 2008. Of that, gas chromatography represents 23%, or about $1.4 billion. Because of gas chromatography's ability to analyze essentially any chemical mixture that can be put into a gaseous state, it has a wide range of applicability across an extremely diverse group of industries. Furthermore, within each of these segments, gas chromatography can be applied in multiple roles. For instance, within the pharmaceutical industry, which last year constituted 34% of the broader GC market, GC is used both in an R&D as well as process or quality control roles. In addition to understanding the size and features of the GC market, it's important that we understand where the market's headed. As you can see, the GC market is extremely mature. Long equipment turnover rate in the industries have created a fundamental shift in the market from providing initial systems to one that provides value-added accessories and replacement parts. This has been signaled in recent acquisitions in the GC market, which have primarily consisted of large existing gas chromatography companies acquiring smaller accessory companies, both for intellectual property as well as their market share, as a way to transition to this industry. Based on industry estimates, or based on industry data, we've been able to estimate there are over 192,000 gas chromatographs in use around the world. Furthermore, based on industry surveys, we think the market would be extremely receptive to an accessory that adds value by reducing the throughput time associated with sampling. Once again, we think there's a demonstrated market for an accessory that can be incorporated into existing gas chromatographs, but reduce sample throughput time. To talk more about that, here's TJ.
Okay, so we know what the market looks like, but how do we get into it? Our first option would be to incorporate Dr. White's technology into a portable gas chromatograph. Although the small oven size would make development feasible, portable GC demand is limited to a small number of industries, such as environmental and petrochemical, so we would be limiting ourselves to a much smaller market. Furthermore, Dr. White's technology offers very fast analysis times, as we've talked about, but these speeds are not as crucial for field testing situations as they are for labs that continuously run tests. Therefore, our technology does not add as much value to the portable GC landscape, so we have ruled this out as an immediate option. We could also use Dr. White's technology as part of a stationary GC. Stationary GCs are used in every industry where chemical analysis is important, and as Buzz explained, our product adds significant value to these GCs. However, Dr. White's technology is not yet ready to be commercialized as part of a stationary GC, so we would have to add significant development costs. Furthermore, industry typically uses these GCs for at least 10 years, while academia uses them for more than 20 years. So from a sales perspective, it'd be a lot better to sell an accessory that could simply upgrade all of these old, slow GCs in use. Thus, we do believe Dr. White's technology would be most valuable as an accessory. As Buzz explained, lab tests have proven its ability to significantly speed up traditional GCs. Ben's market analysis showed that the market for GC accessories and replacement parts is much larger than the GC market itself. And finally, Dr. White's technology is very close to being a commercially viable accessory. So, accessory is the way to go. But should we try to license this technology to a larger company or start our own company? Let's consider 3 important factors in making this decision. First, significant infrastructure would need to be put in place in order to form a spin-out company. In contrast, the OU Office of Technology Development, or OTD, already has the resources in place to seek out and sign a licensing agreement. It would also take a long time for a spin-out company to gain market relevance, whereas if we sign a licensing agreement, we'll realize immediate revenue. Finally, signing a licensing agreement would allow us to put our product in the hands of a company with industry experience and an established customer base. Therefore, the best option for the university is to license this technology to an existing GC accessory company. With this in mind, we've been working with OTD to narrow down a list of potential licensees into those that we find most promising. The companies on the screen are especially notable because they have either a dedicated university liaison or a history of university licensing agreements. We think OTD should begin contacting these companies immediately, as the ideal path would be to sign a licensing agreement as the technology currently stands, or even to enter into a sponsored research agreement with one of these same companies. Still, after talking to several accessory companies, we have determined that in order to increase our chances of signing a licensing agreement, we will need to further refine our product into a more easily reproducible technology. So therefore, Taylor is going to talk about prototype options.
Thanks, CJ.
Yep.
All right, so as you can see from the picture of Dr. White's benchtop prototype on the screen, it is very well developed. However, there are still a few advantages to creating a more refined prototype. With a refined prototype, we're able to increase the technical efficiency of the machine. We also increase the marketability of the product, as it would be more attractive to a potential licensee. And finally, we increase OU's negotiating power in a licensing contract with this refined technology, because we reduce the risk a company faces when acquiring new technologies. So what are these technical aspects we're talking about that need refinement? First of which is the materials used in the heating element. So not only do we need to make the refined prototype aesthetically pleasing, but we need to make sure that all the materials and parts used in its fabrication are commercially viable. Next is the software integration. Dr. White's technology currently runs on a DOS C++ system, which isn't necessarily used in commercial application. And what we've learned from market trends is that companies are looking for one-touch, simple software solutions. So we need to make sure that's integrated into the prototype. And next is the method used for temperature control. And finally, when looking at prototype development, it's important to think about the development timeline and the cost of doing so. So we identified a number of different prototype sources and did research on each. From these, we narrowed it down to 3 companies: Let's Go Robotics, the OU Instrument Shop, and Surtech Medical Systems. Now, we've signed confidentiality agreements and began discussions with each of these 3 companies. From these conversations, we've learned that the estimated time to complete a commercially viable prototype is no more than 6 months. At the same time, the cost was estimated at $86,500. So this cost includes everything from the initial engineering design study to the materials used in development, as long as the software integration and development, any testing or certification the machine might require, and of course the prototype itself. So how does this all fit together? Well, we have Dr. White's GC technology and know that the best path to the market is by licensing it to an existing GC accessory company. So one thing that's so cool about this technology is that beginning as soon as tomorrow, OTD and Dr. White can contact accessory companies in pursuit of this licensing agreement. Now, as TJ said, companies acquire technologies in a variety of different ways, and it's possible that they will be willing to license this technology as is. But what we've learned from talking to the companies is that it's more likely that we will need to develop this more refined prototype before we can reach the licensing agreement. Now, of course, the development of a prototype means funding. And we've researched and identified a couple different funding options and know there's potential application in the OU Growth Fund and a couple of federal grants. Either way this technology is able to reach the licensing agreement, our team knows that Dr. White's technology can add value within the existing GC market. So let's recap. Buzz gave you an overview of Dr. White's technology, and particularly its speed, an ability it has to reduce throughput time and increase the number of samples run in a lab per day. Then Ben gave you a market overview, told you what the market looked like, and about its growth. From this, we've learned that the accessory area of the market is most attractive for our technology. Then TJ looked at development options and how we get this technology to the market, which we know is from the pursuit of a licensing agreement with an existing GC company, which most likely requires the development of a refined prototype. And then we talked about how to take this technology forward. I speak on behalf of the team when I say it's really exciting knowing that technology that Dr. White invented right here on OU's campus has the potential to be commercialized and taken out to the market through the pursuit of a licensing agreement. And on that same note, we'd like to thank Dr. White for allowing us to work with his technology and his patience in helping us understand gas chromatography and the technology at hand. We would also like to thank Chris Mazzell for his support as our mentor throughout this entire process, and show our appreciation to CCEW and our time through this internship experience, and just speak to the everything that we've learned throughout the entire experience, and even the relationships that we've been able to build with fellow interns. So on that note, we'd like to thank you guys for your time and for being here tonight, and we'll be happy to field any questions, comments, or even suggestions you may have. Yes, sir.
You say this new GC is like fast, but how does the quality of the data compare to like the older version?
That's a great question. Just to repeat it, he said, you say that this GC is fast, but how does the data compare to that of the old GCs?
Based on what we've seen so far, the data is very much comparable. However, one thing that would come out during the prototyping stage is analysis of a broader range of chemicals, or maybe more different applications. We'd be really able to verify what we think now is something with a very broad application.
And I would add on to that, because the speed is so much faster, because it's able to heat a lot faster, there's more distinct peaks in the graph of which the chemical comes out. So if anything, it's better. It's higher quality because the peaks are a lot more distinct as they come out of the graph.
Yes, sir.
Either one. Go ahead.
Have you guys thought about what kind of license would be ideal given the current situation, whether or not it would be sort of an upfront payment or something that would have a residual percentage of sales? Have you guys thought about that at all?
He asked if we had thought about what type of license would be best for this technology.
We haven't. We've been working with Dr. Elaine Ham in the Office of Technology Development, and that's sort of something that's probably going to emerge over winter break as we can continue working on this.
Good question. Yes, Dr. Holmes? Good question. He asked if the technology is patented and is currently patent pending, has been assigned a patent examiner, but the examiner hasn't gone through the application yet. Yes, sir.
I know this new technology can improve the temperature about 5 times faster, and it also reduce the temperature, cooling almost 20 times faster. Is there any extra price you can get this all and
He asked about if we can increase the temperature so fast and decrease the temperature fast, does that affect the lifespan of the instrument? Is that what I gather?
That question was actually brought up in our initial meeting with Dr. White. There was some concern that the increased rate of, I guess, temperature change might somehow affect the longevity of the parts. Based on what he's done quite a few samples so far, this has actually been in use for years, and he hasn't noticed a significant change between, I guess, an older GC and what he's been using in his lab with the really rapid temperature change. So the answer, based on what we know so far, is no, that it does not affect the life of the parts.
And just to add to that, the part that's the heating effects is the column, which would be replaceable in each of the machines. And it is an accessory on just existing GC units.
Did you guys do any estimation to see just how much more benefit you'd get out of a license agreement as to forming an outside entity?
He asked if we did any estimates on the numbers of a licensing agreement versus a spin-out. Did you want to address that?
Yeah. As far as the capital requirements go for forming a spin-out company, we don't have the numbers there. Essentially, it's mostly comes down to the feasibility of performing a spin-out as opposed to signing a licensing agreement. And it's a huge it would be a huge advantage to get our product in the hands of a company that already has a huge market share. So,
To add on to TJ's point, essentially the way things are sold in the GC market is very much a vendor relationship with the customer. So that's a huge portion of the infrastructure that would need to be added if we were to do a spin-out company, and that's pretty daunting. It's kind of led us in the direction of the licensing agreement preference.
We have time for one more question.
Michael Linville?
This question has a couple parts, but how many different companies are there producing gas chromatographs right now? Are there a few who control the majority of the market, or how is it set up?
He asked about the companies that are working in the gas chromatograph currently, so what does the market look like and who are the major players?
The gas chromatograph market itself, in terms of the companies who make gas chromatographs, not just the accessories, is dominated by Agilent. They have something like a 35% market share. And below that, it's Varian and PerkinElmer and a few others are right around 10%. And then there's a lot of very small companies that, as far as we can tell, are hoping to get acquired by one of these top 5 to 7 companies.
TJ makes a really important point at the end there. The way that the market is structured is essentially these really large companies that are in the business of producing standalone GC units, the sort of front-to-back service. But there's been all these recent emerging companies primarily in the accessory market. As I mentioned in my marketing portion, these large companies are actually expanding into the accessory market by acquiring some of these smaller companies, and it's really been where the development and growth in the GC markets come from.
So based on that, how difficult or easy would it be to make your device compatible with different kinds of gas chromatographs, different brands?
He asked about the compatibility of the gas chromatograph. And one thing, Dr. White's technology uses the existing injector and detector on gas chromatographs. So it's very easy, and that's when we mentioned the compatibility of the actual technology, because it should be able to connect to any GC with the standard injector and detector. Now, what we have learned, and TJ could touch on more, is about accessories that improve technologies are sometimes taken over by certain companies, and they only fit them to their technology, their standalone GC. So in that case, it would be the company fitting it like the door of the GC, so it only fit on their standalone GCs, but injector and detectors are universally used.
Please join me in thanking Team Garage.
We are extremely proud of this team, as in only 4 months, they have been able to add value in a variety of areas within the university. But in particular, they have found the right niche for this technology in the marketplace, and also established very valuable contacts for the Office of Technology Development going forward. To introduce the next presentation of the night, I would like to welcome Mr. Rod Foster, CEO of Synthesized Nano Coatings, an OU and CCEW spin-out, and also CCEW's Entrepreneur in Residence. Rod's participation in the program traces back to the summer of 2007, when he first mentored a CCEW team, to later on become a CCEW full-time staff member. Mr. Foster has several years of experience in the product development area, and he retired as a senior executive from Baxter Pharmaceuticals. Please help me welcome Mr. Rod Foster.
It was my privilege this semester to co-mentor the team that we call SWINT, and named after the company, the Norman company, that was formed to develop nanotechnology and single-wall nanotubes. And co-mentor with Dave Arthur, who's here this evening. And Dave, thank you very much for your support and your management team support. One of the things that this team had a few different challenges. One of the things that we knew that was going to be particularly difficult, based on having had a previous nanotechnology team, is that nanotechnology is still developing as an industry, and there aren't a lot of associations and organizations that you can go to and get a lot of historical data. So we knew that the team was going to have to do some digging and would learn a lot from SWINT and the management team there in order to come up with the answer to the question that they were challenged with. I'll let them tell you about challenge in their presentation. But I wanted to also let you know a few things that were kind of interesting about this team that were different from other teams. Is there was an existing company in place, and they had a challenge to address a particular aspect of increasing sales for that company. So many of the teams start with a blank sheet of paper. This team started with an existing company and a specific challenge to help that company. They are going to end not only with the presentation tonight, but they will be making a presentation tomorrow to the SWENT Board of Directors, where they will go through their recommendation and talk about why they came up with the answers that they did. So that's kind of a unique experience as well. Not many of the teams will have an opportunity to have that FaceTime with the Board of Directors and to hear the questions asked and to give that some thought. You know, through the course of the semester, like any team, they all kind of begin with this as a new technology. It's something they're having to learn about through that boot camp that we talked about, and then they kind of take it from there, either plant tours in the case of SWENT. They may do a lot of research. I think people find that the teams are really great at coming up with articles and digging and finding information, having some great follow-up phone calls with people and gathering information. This particular team, you know, it seems like one semester, one team has an opportunity to make a road trip. This was the road trip team this semester. They had an opportunity to go up to a composites conference, and they'll tell you a little bit more about composites. That's one of the, there's a whole new language in this nanotechnology area. And so they were the road trip team. They got up at early and left at 6 o'clock from Norman one morning and went off to Wichita, where the conference was, and came back that night. So, you know, I went along, and I thought we would have a hard time using our time. And one of the things I found is that at the end of the day, we had only talked to about half the people that we had intended to, because there was so much information that the team was gathering that it, you know, just turned out to be a great trip. In addition to that, you know, you always learn something that's kind of close to the technology or maybe not. In this case, it was, I think there was a major discussion around the quality of I think it's a Quick Trip slushie versus a 7-Up, 7-Eleven slushie, or, you know, something like that. So another pretty technical, maybe a future project. So I guess I wanted to say that the teams have fun in addition to doing a lot of hard work. And with that, I will turn it over to Team SWENT.
Oh, no. Good evening. Tonight we will be presenting a new technology which incorporates carbon nanotubes into an innovative material. My name is Lucas Rice. I'm an industrial engineering sophomore from Fort Gibson, Oklahoma.
My name is Austin Slaymaker. I'm from Blanchard, Oklahoma, and I'm a political science and international studies junior.
My name is Sean Bramble. I'm a finance and accounting senior from Tulsa, Oklahoma.
My name is Yunfei Li. I'm a chemical engineering senior from Hebei, China.
Our team leader is I-CCEW alum Blake Trippett, and our mentors are Dave Arthur, the CEO of Southwest Nanotechnologies, SWENT for short, and Rod Foster, the CEO of Synthesized Nanocoatings. Currently, Southwest Nanotechnology is the world's leading manufacturer of carbon nanotubes. They have been able to achieve this level of success due to the consistency and high quality of the carbon nanotubes they produce. Well, what is a carbon nanotube? Basically, carbon nanotubes are sheets of carbon 1 atom thick that have been rolled into a tube. These structures are 50,000 times thinner than human hair. Despite their small size, they exhibit some remarkable properties. For example, carbon nanotubes are more electrically conductive than copper, 10 times lighter than steel, and 250 times as strong. SWENT has hypothesized that processing carbon nanotubes into a paper-like material could allow them to enter into previously unreachable markets. As it turns out, this carbon nanotube paper is in the early stages of development in research facilities and has been given the name Bucky paper. SWENT is specially positioned to take advantage of this Bucky paper opportunity. They have recently released a new type of carbon nanotube. These specialty multi-wall carbon nanotubes offer a unique combination of quality and cost that would be well suited for use in Bucky paper. Bucky paper maintains all of the qualities that make carbon nanotubes remarkable. Because of this, it has some obvious market potentials. For example, bucky paper could be used to make armor plating for tanks that would allow for an improvement in strength and mobility. Or it could be laid down as a structural support in bridges. Our team's mission this semester was to analyze Swent's hypothesis concerning bucky paper's ability to facilitate carbon nanotube usage in new markets. During this presentation, we will walk you through the steps we used to do this analysis. First, we researched into the opportunities available to bucky paper. This consisted of analyzing potential markets, paying special attention to the time to market and profitability of each. Next, we researched the technology to see at what scale and quality current methods could produce bucky paper at. And ultimately, we came to the conclusion that bucky paper in its current form is still a developing technology and inherently has a large number of unknowns and other risks. After walking through this process, we will then give our recommendation as to how Swent should position themselves to best take advantage of this developing technology. With that, I will hand it over to Austin, who will go through our market analysis.
Thanks, Lucas. All right, so as Lucas mentioned, our mission for Swent this semester was to investigate the potential opportunities of bucky paper. With such unique qualities, you can imagine that the market opportunities for bucky paper are vast. We identified 7 markets on which bucky paper could serve. We evaluated these markets on many factors, including the time to market, or the time after which the material will be certified for use. This is quantified on the x-axis. Another metric we used was the overall attractiveness of the market. This included things such as the market size, the competitors within the market, any market need that there was, and any price sensitivity of the customers. You'll notice that the highest potential markets will appear in the upper right-hand quadrant. The 7 markets that we researched included heat sinks, recreational equipment, automotive, electronics, aerospace, defense, and bridge construction. You can see that defense and bridge construction turned out to be the highest potential markets. So let's look at those a little bit more closely. After analyzing these 2 markets, we found bridge construction to be a more appealing market than defense based upon a shorter time to market and though only half the size, still presenting a large enough financial opportunity. Bucky paper is being researched and developed within the Department of Defense. This indicates that there may be a high amount of competitors within the defense market. And finally, bridges are presenting a pressing problem in this nation. So let's look a little bit more deeply into that problem. So like I said, there's a significant problem with U.S. bridges today. For headlines far too often report of collapses happening around the nation. The bridge in front of you is of the Minneapolis bridge collapse in August 2007. This took the lives of 13 people. You see, bridges and highways were built decades ago during a past era of public works. Bridges were built using concrete because advanced materials did not exist. Today, bridges are nearing the end of their useful life because of widespread corrosion of this concrete. And this corrosion is affecting many bridges. In fact, the Federal Highway Administration reports that 160,000 bridges, or 1 in 4 bridges that you and I drive on each day, are damaged and in need of repair. These bridges are categorized as being structurally deficient or functionally obsolete. In fact, the Minneapolis bridge was classified as such before its collapse. Another difficulty in this is that repair time or installation of a new bridge is quite lengthy. Well, today, the U.S. is moving forward and looking forward into a new era of public works. The new administration is placing emphasis and providing funding for an update of the American infrastructure. Unlike the past, today we can incorporate 21st century technologies to help solve the bridge problem that we have. In fact, the U.S. government is actively seeking innovative technologies to help bridge our problem. So, materials in bridges will be particularly valuable if they resisted corrosion, extended the life of a bridge, and will be able and were able to be installed more quickly. I'm going to turn it over to Sean to talk about a technology that's meeting these characteristics and to talk about how Bucky paper fits into this picture.
Thank you, Austin. So as you can see, there's a huge problem with bridges in the United States, and it turns out that a material known as a fiber-reinforced polymer is beginning to alleviate it. Fiber-reinforced polymers get their name from the glass fibers that make up their core ingredient, and they've recently been used to make technologically superior bridge deck panels. Oh, excuse me. This is a picture of an FRP deck being laid into the ground. As you can see, FRP bridge decks offer a number of benefits over traditional reinforced concrete decks. First, they resist corrosion, allowing them to last upwards of 100 years. Next, they're extremely lightweight, allowing installation to take days instead of weeks or months. And finally, with reference to price, it turns out that the government requires FRP companies to make their products significantly thicker than is needed in bridges. This is because FRPs haven't yet been validated for widespread use in the marketplace, and it translates into their prices being twice as much as reinforced concrete decks. This price is so high that we're only seeing FRPs used in situations where grant funding is available, and this creates a lot of competition among FRP manufacturers for government bids. Here's where Bucky paper comes in. Bucky paper could potentially be integrated into fiber-reinforced polymers to provide a competitive advantage to the company that uses it. This is because Bucky paper's electrically conductive properties could allow it to validate the integrity of FRPs over the long term. This was done through a process known as health monitoring. Health monitoring could eventually bring the price of FRPs down to where we could see them in projects that aren't using grant funds. Health monitoring works like this. Devices are attached to each end of a bridge that monitor the electrical resistance over the Bucky paper coated portion. As the bridge encounters damage, the Bucky paper is deformed, changing its electrical resistance. By monitoring this electrical resistance, bridge technicians can pinpoint the exact points on bridges where damage has occurred and conduct preventative maintenance. So clearly, health monitoring adds a benefit to FRPs, and it also provides a big opportunity for Bucky paper. We found that this opportunity could materialize over 2 phases. In the short term, Bucky paper could be integrated into fiber-reinforced polymers in the way that I've talked about and provide health monitoring functionalities. This added benefit won't likely allow their manufacturers to charge a higher price. Rather, it would be seen as a marketing expense, as it could help them win more government bids. After talking to a number of companies, Swin has found that they could charge about $12 a square foot for Bucky paper. This is extremely attractive when we realize that the key ingredient in Bucky paper are the carbon nanotubes. If Swint sold an equal amount of nanotubes in their raw form, they could charge about $4. But since they've been put into a more usable form, they can charge 3 times as much. Next, you'll also see that the costs associated with producing Bucky paper are a little bit higher than with nanotubes in the raw form, but we can still make 4 times the profits of selling nanotubes alone. Now, I should probably mention that the margins you see here for nanotubes aren't Swint's actual margins, as this information is confidential, but they have been based on margins typical of high technology companies. Once again, in this short-term phase, grant-funded projects will be targeted, as the price of FRPs is still too high to be used in other projects. Over the long term, Bucky paper could potentially bring the price of FRPs down. According to the National Composite Center, they need to be priced at about $75 a square foot to be used in situations where grant funding isn't available. This represents a 25% premium over the price of reinforced concrete decks. One way this could happen is if Bucky paper is successful at validating FRPs for long-term use. If this happens, the increased confidence will allow their manufacturers to significantly reduce the thickness of their products, which will bring prices down. Now, at this point, Bucky paper will have served its purpose in validating FRPs, and to remain viable, it must take over a portion of the FRP material. During this phase, the volume of projects will significantly increase as we can target non-grant funded projects. Now, to be integrated into FRPs, Bucky paper must first meet a number of technological specifications. Theoretically, it can already do this, but in practice, results have varied. Next, I'll turn it over to Yunfei to talk about the current state of the technology and the risks that it presents.
Thank you, Sean. So as you can see, there is potentially a great opportunity for bucket paper in the bridge decking industry. However, before bucket paper is ready for the market, there are a few technical requirements bucket paper needs to meet, and these are the cost, scale, quality, and health monitoring capability of bucket paper. Let's start with the cost. Just like Sean mentioned earlier, in the short term, bucket paper and FRP bridge deck will cost about twice as much as traditional concrete decks. However, in the long term, in order to reach a wider market, the price of FRP and bucket paper bridge decks must come down significantly. At the same time, it is important that bucket paper has a scalable manufacturing process. Currently, there are two leading bucket paper manufacturers, and they are Florida State University and Buckeye Composite. And of the two, Buckeye Composite currently has the most scalable manufacturing process achieved. So with that in mind, government typically give about 3 months before all the material for the bridge project is required. So if we were to use Buckeye Composite's methods to do a bridge that's 200,000 square foot, it would take them 1.5 years to make all the material for this project. As you can see, a much more significantly scalable process needs to be developed. At the same time, bucket paper needs to be produced at a quality that's equal or better than current FRPs. Of the leading bucket paper manufacturers I mentioned earlier, Florida State University currently has the best quality bucket paper achieved. So if we compare their bucket paper to current FRPs in strength, which in megapascal, which is the unit measurement of strength, we see that the quality of bucket paper is not there yet. Theoretically, bucket paper can be much stronger than current FRPs. However, the technology needs further refining before this goal is attained. And lastly, with reference to health monitoring capability, there has been limited lab studies done that showed inconsistent results for bucket paper showing health monitoring capabilities. So as a result, further technology development and testing is needed to see how bucket paper will truly perform after it's been integrated into composite decks. So as you see, bucket paper could potentially be a more marketable form to sell carbon nanotubes. However, the technology is still maturing. With that, there are a few key risks. And these risks are the technical, market, and financial risk. In the technical risk, just like I mentioned earlier, none of the current technology meets all the technical requirements I mentioned earlier. And with that, there is inconsistency in health monitoring testing. In the market, there's risk of whether or not FRP bridge deck manufacturers will truly value the added benefit of bucket paper, also whether or not if they're willing to adopt it into their bridge deck. Also, the assumptions we have made in our opportunity assessment need to be validated. And last, in our financial risk, because none of the manufacturing method is up to par, there is unknown capital expenditure associated with producing bucket paper, and with that, the profitability of the project is also unknown. So now you have a better understanding of where the technology actually is, and also the risks associated with that. I'll hand it off to Lucas to provide a recommendation.
So given the facts that bridge decking presents a lucrative market, but bucket paper in its current form is still in the early stages of development, we recommend that SWENT maintains their relationships with Buckeye and FSU in case either of them develop a more scalable method for producing a high-quality bucket paper. SWENT should also consider the possibility of developing a new method of manufacturing bucket paper internally. This would be advantageous because it would allow them to pursue patents and ultimately avoid licensing fees. When evaluating new methods for manufacturing bucket paper, SWENT should pay attention to SWENT should evaluate them based on the following metrics. First, the method must be capable of producing enough bucket paper to build a bridge in under 3 months. The bucket paper produced must be at least as strong and durable as current FRP products and can cost no more than a 25% premium over current reinforced concrete when installed. On top of all of this, the bucket paper must also offer a stable form of health monitoring. If a technology is found that meets these requirements, SWENT should consider partnering with a prominent FRP manufacturer. We believe relationships with companies such as Martin Marietta, Zelcomp, Composite Advantage, or Creative Pultrusion would all be beneficial because these companies have all done work and are the leaders in the grant-funded fiber reinforced polymer bridge decking industry. SWENT should also evaluate other markets. Although bridge decking is currently the most lucrative, defense also ranked highly in our analysis, and the heat sink industry will likely see an increase in demand as computer processors continue to become faster and more powerful. In summary, our market analysis has shown that bridge decking is currently the most lucrative market for Bucky paper, but the technology available is simply not scalable and does not produce a high enough quality Bucky paper. Because of these technological shortcomings, there are a large number of risks associated with pursuing Bucky paper in its current form. Because of these risks, we recommend that SWENT does not pursue Bucky paper through current manufacturing processes, but should instead focus their attention on finding a method of manufacturing Bucky paper that meets the aforementioned metrics. Well, we hope you have found our presentation informative and have learned a little bit about the bridge decking industry and Bucky paper, and we will now take questions.
Aside from defense, which you mentioned, what are some of the other commercial uses of Bucky paper currently?
So the question is, what are some of the other uses for Bucky paper commercially?
There are some, for example, in aerospace, Bucky paper can be used on the airplane to serve as lightning protection. Currently, airplanes, they use a heavy metal for that purpose, so that would lead to a lot of fuel costs. So Bucky paper is very light, so if Bucky paper could replace that metal mesh, because Bucky paper is very electrically conductive, that could save the aerospace industry a lot of money. Also in heat sinks, because of processors are upgrading, so there needs to be a high thermal conductive material that can dissipate heat faster. And do you guys have anything to add?
I would just add that there's clearly a lot of potential applications for Bucky paper, but it's not actually being used anywhere yet. It's still kind of in research and development.
But to add on to that, it's been looked at to potentially use it within the defense market, not only for armored vehicles, but also for body armor, where the packs that the soldiers wear can be significantly lighter, but still they can remain protected.
Based on the graph you guys had about the number of bridges that are in the state of disrepair right now, what can you tell me about the rate at which funds are being made available for these repairs? Even if Bucky paper was 100% right now, is that a market that all the 175,000 bridges that are disrepair, those would be immediately available? Or is it things that funds are released in small portions over time, so the market is sort of contingent on federal or state funding bridges?
So the question is, what kind of funds are available for bridges, because they are, failing?
So the American Society for Civil Engineers, they report that $10 million every year is spent directly on repair and replacement of these structurally deficient bridges. With the stimulus occurring, it appropriated $50 billion to the infrastructure, and of that, $27 billion directly for bridges and highways. And today, the President gave a speech over jobs and also talked about using some of the TARP money to help with our infrastructure, specifically for our bridges and highways. In regards to the money for Bucky paper, I'll let someone else take that one.
Yeah, I can add to that. So basically, right now, the amount of grant-funded projects is a small number in comparison to all the bridge projects going on right now. Basically, there are some indications that the opportunity for Bucky paper and FRPs will increase as we go forward. There's actually what's called a composites caucus forming right now, and they've been lobbying Congress to actually make 10% of bridge projects focus on net present value. I showed that clearly FRPs are a lot more expensive than reinforced concrete, but actually over their lifetime are a lot cheaper. So this could kind of increase the opportunity in the short term.
Is there information available on the safety of this material for workers, the environment, disposal when it's spent?
On the Bucky paper? Okay, so the question is over the safety concerns of Bucky paper and carbon nanotubes.
Composites and bridges, or FRPs, are actually more environmentally friendly than using concrete. And part of this comes from the quickness in which you can install them. As far as safety goes, clearly they're a lot stronger than reinforced concrete. Were you referring to safety in installation or safety just in the bridge itself?
Well, I'm thinking of asbestos. It was the greatest thing since sliced bread a long time ago, and now we find out it's got health consequences. So I'm just curious what the
I
state of
see.
research is on the safety of this material.
Bucky paper or FRPs?
The Bucky paper.
Bucky paper. There are ways of making the Bucky paper very safe. It uses carbon nanotubes, but as long as you can kind of trap those within a structure, it's extremely safe. Do you guys have anything to add to that?
Well, there's no information that indicates carbon nanotubes are potentially dangerous to health. And our team mentor, Dave Arthur, recently gave a presentation discussing the health effects of carbon nanotubes, and he could maybe answer that better than we can. But yeah, as of now, there's no information.
Is it too early to tell when technology will catch up with the market? Will it be like 5 years, 10 years before Bucky paper start being mass-produced at the level which it needs to be?
So the question is over how long will it take for Bucky paper to be able to be produced at a scalable level?
I guess currently we don't really have the ability to tell the exact time, but it could be from anywhere from months, maybe years. Do you guys have anything to add?
Articles that talked about Bucky paper that we looked at and read indicated that FSU in particular expected to have a scalable process within a few short years. However, this article was from a few years ago, and today they still do not have a scalable process. So it's just an unknown and therefore a risk.
Any last questions? Is the Bucky paper the only solution for future interlayer of the FRP? And also, for me, currently it's like a paper form. Is there any form like powder that you can do spray? Then you can save more material and make it even cheaper. And for current bridge, not future bridge, can you spray or do you have some other insert technology make the nanotube into the FRP that you don't need to spend so many nanotube, just a slight amount of nanotube can make the bridges very strong?
So the question basically had two parts. First of all, he was asking if there is another material that could be used in FRPs instead of Bucky paper. And the second part of the question was, is there another way of dispersing carbon nanotubes other than Bucky paper?
So carbon nanotubes are currently in powder form. And they do have that spray application to them. However, with that, there are some problems such as the carbon nanotubes, they tend to clump together, which can be very difficult for industrial applications. And so Bucky paper in a paper form solves that problem. So that's why carbon nanotube as a powder form can't be used in bridges directly. And I think Sean has something to add to that.
Yeah, the real opportunity for Bucky paper and bridges really starts out by kind of providing the means to decrease the panel thickness. As I said, the real problem is the cost, and actually what happens when there's a thick FRP panel, it takes a lot of resin to fill in the spaces between the glass fibers, which really drives up the cost. And so Bucky paper at first can validate FRPs and they can reduce that thickness, but also if it takes the place of some of the FRP, it can really reduce thickness further and reduce price. So does that answer your question?
Please join me in thanking Team Swint.
We would like to thank our mentors really quickly. That without their guidance and advice, we would not have been able to figure anything out with Bucky paper. And we'd also like to thank CCEW, because I'm sure I speak for all of us when I say this was a wonderful experience and it has benefited us greatly.
Yes.
Thank you.
Thanks.
We're particularly proud of Team Swent since at the beginning of the semester they faced a difficult task to find the best short-term opportunity for an emerging technology. And in 4 months, they managed to add value to Southwest Nanotechnologies by identifying this opportunity and also identifying clear metrics for commercialization and adoption success as this technology continues to evolve. To introduce the last presentation of the night, I would like to welcome Mr. Bill Avon, Principal at Avon Enterprises and CEO of Game RNA. Mr. Avon has several years of technology commercialization and product development experience as former Director of Technology Transfer for the Oklahoma Medical Research Foundation and also a Vice President for Health Technologies. Please help me welcome Mr. Avon.
Ever since Mariana asked me to give this introduction, I've been trying to think how to share with you the challenges that this team faced, especially at the get-go. So I've gone back, way back in my education, and have pulled a line out of a poem that I had the opportunity to translate. I apologize if my accent makes this indistinguishable. But let's start off with Menen aede pleiades lexios. No? No understanding? Okay, well, let's switch gears then. How about Fresnel diffractions? Differential diagnostics? Field emission X-ray tubes? Cancer? Okay, cool. I finally saw some nodding heads. Cool. Well, just as Homer and other poets started from that prayer to the muses and fates and built up a comprehensive and compelling story that has been translated into what we now call the Iliad, so too has this team of young professionals translated Dr. Hong Lu's fascinating patented, who asked the patenting question, patented technology into a comprehensive and what we hope is compelling story about how CCEW and the university should move this technology along. And yes, 16 weeks ago, it was all Greek to them too. Sorry, that's why I had to go back to the Iliad. I needed a joke. But you may actually hear a non-scientist use the concept of sensitivity and specificity and know what it means. Pretty cool for someone in the College of Letters. Now, this has been a great honor to work with this team, to work with the entire group. You've got a wicked smart Apollo, a wise and sensitive Athena, even a blustery yet benevolent Poseidon. This has been a lot of fun. It's a good group. The kids who are laughing, they know who I'm talking about. Daniel's sitting down here laughing too. He knows who I'm talking about. Thank you very much. Thank you. Rod, you hooked me into this. Thank you, sir. Ladies and gentlemen, I'm not going to steal any more of their thunder.
Hello, everyone. Excuse me for a moment while I pull up our presentation. Oh, there it is. Sorry about that. Okay, well, hello, everyone. I'm here with Team Inline Imaging. My name is Vin Pham, and I'm a senior chemical engineer from Oklahoma City.
My name is
Holly Rowe, and I'm a senior letters major from Tulsa, Oklahoma.
My name is Ryan Reber. I'm a senior entrepreneurship and finance student from Lubbock, Texas.
I'm Toby Olushola, an industrial engineering and pre-pharmacy senior from Nigeria.
And first, we'd like to acknowledge our inventor, Dr. Hong Liu, who's a professor of computer and electrical engineering here at OU. Also our mentor, Bill Avon, principal at Avon Enterprises, and our team leader, Ms. Samantha Ali, who's a psychology major originally from Brighton, England. So our team is here to present to you an X-ray imaging device for soft tissue. Now, there's a big need for advancement in the medical imaging industry, and that's where Dr. Liu's technology can come in. Because you see, in the 115 years that have spanned since X-rays were first introduced, there's been quite a bit of improvement in terms of bone imaging. You'll see on the right that it's quite a bit clearer, and you can see some nice details. But in terms of soft tissue imaging, there hasn't been quite the same advancement. Now, about 40 years ago, they did introduce computed tomography, which you may be better known as CT scans. But with these scans comes a lot more cost to the clinics and a lot more cost to the patients. And on top of that, it increases the radiation dosage by nearly 100 times the amount. So this really limits the applications of CTs for regular screenings. So how can we provide better images of soft tissue without the high cost and high risk? Well, let's look at technology used today. You'll see that there's basically an X-ray source, the object you're trying to look at, and the detector directly behind it. Now, as you allow the X-rays to pass through the object, the detector picks up those X-rays and provides the image you see on the left. So it's not a very clear image, and it's really hard to see the details. So for radiologists, this can be a big problem. Sometimes it may lead to false readings and can lead to misdiagnoses, which is a huge problem in the industry today. However, with Dr. Liu's technology, we can include an air gap. And with this, we take advantage of what's called phase contrast imaging. It really clears up the image, as you'll see on the right, and increases the contrast that you'll see between objects. So as you see here, for radiologists, this means better tissue boundary interface and can increase better readings and better diagnoses. This reduces the need for unnecessary additional procedures, which would add to the cost of the patients and increase the additional dosages to those patients. But on top of that, we can include a second detector. And with this, with one radiation exposure, actually provide two images, combine them with a unique algorithm, and provide a third image that's not only very clear, but provides information such as the density of the object you're looking at. So what this ultimately means is that a radiologist can look at a tumor and actually determine whether or not that's benign or malignant. So as you see, there's a huge need for this kind of advancement in technology today, and Dr. Liu's technology not only solves that with a unique low cost and low risk solution, but really sets the bar for what X-ray technology can do today. So now that you better understand how his technology works, Holly will tell you more about the added value of Dr. Liu's technology.
Thank you. Dr. Liu's technology, like Ben mentioned, has a lot of value that can be added in terms of medical imaging. First, Dr. Liu's technology creates a better image. This image increases specificity and sensitivity, which in turn enhances soft tissue boundaries. This is an area of improvement that greatly appeals to radiologists today. This better image quality allows radiologists to identify whether abnormalities, such as tumors, are benign or malignant with more accuracy. This in turn enhances the overall patient-doctor diagnosis. Furthermore, Dr. Liu's technology has the ability to create this clear image at a much lower radiation. Studies indicate that excessive radiation exposure to the patient actually increases their risk for getting cancer. Now, Dr. Liu's technology can significantly reduce this radiation exposure. Furthermore, Dr. Liu's technology can be easily implemented into current clinical systems, as it looks and functions similarly to current medical imaging devices, and can also be used by technicians with minimal training. This is a huge reduction in doubt for hospitals, as it reduces the doubts they might have in replacing their current medical imaging equipment. This overall value comes at a much lower cost to hospitals and patients by reducing unnecessary screening. Now, not only can Dr. Liu's technology dramatically cut costs, but this technology has the potential to save lives. Now that you understand a little bit more about how the value of Dr. Liu's technology could have in terms of medical imaging, let's take a look at what this medical imaging equipment market looks like. the United States medical imaging equipment market, according to BCC research, is about a $9 billion market. Now, like Vin mentioned earlier, because this technology has the ability to increase soft tissue boundaries, it was the focus of our team to look at a specific type of medical imaging, mammography. Mammography occupies $457 million of this $9 billion market. It's projected to grow at 3.6% annually, reaching $585 million by 2015. Mammography continues to be the gold standard in early detection for breast cancer. And with an aging U.S. population, specifically women who are reaching the ages of general annual mammogram screening to increase by about 13% over the next 5 years, we see the impact that Dr. Liu's technology can have in terms of mammography, and strongly recommend entering this innovative technology into a growing mammography market. And with that, I will turn it over to Ryan to show you how.
Thanks, Holly. So the mammography market has its fair share of problems. As you may have seen in the news lately, mammograms are riddled with misdiagnosis, or false positives and false negatives. Now, a false positive occurs when you get screened by a mammogram and it actually detects cancer when there isn't any present. A false negative is the exact opposite. The machine will actually miss cancer when it is actually present. Now, let's take a second and focus on false positives. When false positives occur, additional screening is required. These tests include a diagnostic mammogram, ultrasound, and MRI. Now, these tests can be extremely stressful for patients and at times dangerous. On top of that, they can be very expensive. The average cost to run these additional tests is $1,700 per patient. Now, according to the American Cancer Society, 63 million mammograms will be performed this year. That means there's a lot of additional testing going on. And due to false positives, there's a high significant cost due to that. The current medical industry spends about $12.8 billion a year on unnecessary screening. So Dr. Liu's technology has the ability to reduce false positives. Therefore, we can reduce the amount of additional screening, significantly lowering this amount of money that is spent on unnecessary screening. So how do we take this innovative technology to the patient? Well, let's take a look at how this market works. A technology like ours can enter the market in one of two ways. The first being a startup is formed around this technology. A prototype is built, manufactured, and then sold directly to hospitals. The second option being that technology is directly licensed to major companies that are already in the market. So who exactly are these companies in the market? We have found that the large majority of the market is consumed by very large, well-established companies. These companies' latest innovations within the mammography field have come from taking their old systems from a film system to a digital system. Now, Konica Minolta is one of those large competing companies. However, they have seen the benefits of phase contrast imaging. They currently have a phase contrast imaging medical device waiting to enter the FDA pathway. The remaining percent of the market is comprised of small emerging companies. These companies have also incorporated phase contrast imaging technologies into their mammography machines. So where does Dr. Liu's technology fit into this market? Do we fit in better as a startup, or do we fit in better as a license? Traditionally, in this market, it is very hard to compete with these very large, well-established companies. Therefore, we recommend that a licensing agreement is the best route. Hologic, GE, and Siemens are very compelling licensing partners because they do not have a phase contrast imaging device. So why would they want to license our technology? What value do we have over other phase contrast imaging technologies? Across the board, phase contrast imaging can provide a better image. This is truly the next innovative technology that is going to change this market. Dr. Liu's technology can be a part of that change. Dr. Liu's technology is patented, as we mentioned, and that patent was issued in August of 2008. The other technologies are patented as well. Now, Dr. Liu's technology can really outpace itself against the competitors in areas of cost and radiation. Now, these traits give us a unique advantage that will appeal to a wide area of the market. This is truly an innovative technology that is going on in a very exciting market where companies are desperately trying to hold on to their market shares and grow. Now, we do recognize that our technology has some issues with development, and I'm going to turn it over to Toby to tell you about some of those stages of development.
Well, What milestones must OU go through to get this particular technology to the patient? Well, since it will be used on human beings, Dr. Lewis' device must be cleared by the Food and Drug Administration. Now, I know many of you here may be familiar with the long and expensive FDA pathway for drugs. Well, the pathway for medical devices is very different, so let's cover that in detail. Now, as a Class 2 device, Dr. Lewis technology is subject to the 510(k) pre-market approval process. The two main parts of that process are prototype development and the specific steps necessary to get to FDA clearance. The first step in that pathway is developing a preclinical prototype. Dr. Liu currently has a working benchtop prototype. However, its results are not sufficient enough to move us forward in the FDA pathway, so a preclinical prototype is required. That development will require $400,000 in about 3 months. After that, we can identify a predicate and begin preclinical testing. Now, a predicate is any other currently legally marketed device that's similar to our device, that's already gone through the FDA process and would be comparable. We can do tissue studies and phantom studies to show how our technology compares to that predicate. That process will cost about $600,000 and it will require 6 months. Now, at this stage, a decision point is reached. OU could either license this technology to one of the larger companies that Ryan talked about earlier, or if OU saw value in this technology as a startup company, it could move forward and develop a clinical prototype. That prototype will have software capabilities and could be used for in vitro studies. Development will cost $500,000 and will require an extra 6 months. And after that, clinical testing can be done. Those will include human studies and density correlation studies, and that will cost about $1 to $2 million and it will require 18 to 24 months to complete. Now, the results of all these tests and studies will be submitted to the FDA, and a decision will be made on substantial equivalence. SE clearance indicates that the submitted information has shown that our device is at least as safe and as effective as other similar devices already in market. Now, overall, this FDA process will take about 3 years to complete and will require about $2.5 to $3.5 million. Now, how do we plan to get that money? Well, the team has identified several sources of funding to get us up through preclinical testing. At this stage, as you can see, for only $1 million in about 9 months of development, we can increase the value of this technology to where it would be attractive to other licensees. Now, after that, if OU saw value in developing this technology further, we've also identified other sources of funding, including those that are specific for small businesses. Now, as I mentioned earlier, prototype development is the first step in moving forward in this pathway. So we've identified 3 different companies that could accomplish this. The first of these is Plexus. They have extensive experience in developing prototypes for several industries and have a successful rapid prototyping program. The second company is Certec Medical Systems. They have experience in developing medical device prototypes and more specifically, Class 2 and Class 3 medical devices. For example, they've even developed other X-ray and mammography machines in their ISO-certified and FDA-registered manufacturing facility. The third company is Let's Go Robotics. They focus on the robotics and automation industries, and they have a successful design to delivery program. After extensive analysis of these 3 companies, the team has already established contact with the CEO of Certec Medical Systems and with other representatives from that company. And we recommend that OU continue to develop that promising relationship and partner with Certec to develop and design a prototype for Dr. Liu's technology. Now I'll hand it over to Vin to talk about what we've done and what we plan to do in the future.
Thanks, Toby. Okay, so now that Toby's taken you through the FDA pathway, let's re-examine how OU can take Dr. Liu's technology from concept to market. First, OU will need to obtain nearly $1 million in funding, and part of this will go to building a prototype. This prototype will be used for preclinical studies. Now, the OU Cancer Institute has expressed interest in partnering with Dr. Liu in order to both develop and conduct these studies at their facilities. At the end of these studies, this will provide a proof of concept, which really adds value to Dr. Liu's technology and puts OU in a position to consider licensing to larger companies, which, as Ryan mentioned earlier, would be Hologic, GE, or Siemens. Once this is done, we recommend that OU pursue other markets with Dr. Liu's technology, and more specifically, other areas of radiology. His technology is already well developed for imaging soft tissue, and this can be applied to many other areas besides mammography. So our recommendations are for future I-CCEW teams, they need to develop a funding strategy in order to come up with nearly $1 million. So this will help them continue prototype development with Certec Medical Systems. They also need to further a relationship with the OU Cancer Institute in order to begin designing a preclinical study. Lastly, they need to establish contact with Hologic, GE, and Siemens in order to build a good foundation for possible future licensing agreements. So ultimately, we want to show that the mammography field is a really exciting area that's really growing and dominated by a number of companies that are really trying to keep their market share. And they do this by acquiring emerging technologies, such as Dr. Lu's technology. So with roughly 1 year time and $1 million, OU can take Dr. Lu's technology into the market. So with that, we'd like to thank Dr. Lu for giving us such an interesting technology that made us learn so much over this semester. Our mentor, Bill Avon, who spent lots of time, late nights, away from home to help us out. And Ms. Samantha Ali, who's taken us further than we thought we could go. And we'd like to thank you all for being here today, and we're open to any questions that you might have. Up at the top.
The difference in radiation between standard radiography and also CT. Can you speak to the comparison there between this technology and those?
Sure. So the question is, how does the radiation from CT scans compare to the radiation from regular technology used today? Sorry about that. So to better understand that, you need to understand how CTs work. Basically what they do is they take the original technology and they basically circle it around the body. So it's like taking one X-ray image, but doing it 100 times around the body to get a 3D image. So that's why it increases the radiation dosage by nearly 100 times the amount.
How does Dr. Lu's technology compare to standard technology?
So how does Dr. Lu's technology compare to today's technology? Well, we don't have exact numbers because that kind of depends on how the development occurs and with the prototype development. However, he's published many studies that are widely accepted, and these studies show that he can decrease the radiation amount substantially compared to what's used today.
What kind of activity has there been between some of the larger companies and some of the smaller companies as far as mergers and acquisitions that have been?
Yes, these companies have a history of acquiring smaller companies. They like to shop around for the best price that they can get. So, I mean, they look at licensing as probably the best route for them to go because they can get it for a cheaper value. Startup is a little bit more expensive for those companies, but they generally like to shop around and find the best deal that's possible for them. Does that answer your question? Okay.
Any other questions?
Let's thank Team in Mind.
I think that's, as all our teams are, another just fantastic example of the quality of work that's being performed here at the University of Oklahoma by our wonderful students. Tackling the 510K process was actually a new venture for CCEW. We've done a lot of traditional drug discovery work, and we understand the traditional FDA pathway that was mentioned, but not only did they explore that on behalf of their own team, but that's knowledge that can be institutionalized here at the university for other like device technology. So they're also establishing wonderful knowledge going forward. So a couple of observations tonight. First of all, I'm really pleased to see the community commitment to the program. We've talked a lot about the various stakeholders here at the university, and the students and the faculty and alumni, but as I look across the crowd and I see the Dean of Architecture and Business and Engineering and Earth and Energy and the Chair of the Research Cabinet and the head of the Oklahoma Center for the Advancement of Science and Technology and leadership from our partners at I-CCEW of Innovation to Enterprise and board members and on and on and on. I think it really shows the community's commitment to, again, this growth and diversification of Oklahoma's economy and the backing and support that we put behind our young talent. So thank you to all community leaders who spent time with us tonight. Your investment, I hope, was was rewarding. I want to end tonight again by talking a little bit about the road ahead in the future, and we alluded to our new interns. What I didn't say was they're going to come from 4 different states, 6 if you count some of our team leaders, 2 continents, 5 different colleges, and sorry guys, their GPA is 3.85, not 3.77. So I don't know, maybe the competition's on. But anyway, they're just really fantastic young intellectuals. As I read your name, please stand up and be recognized. Madison Blocker, International and Area Studies. Amy Henderson, Marketing. Rojo Liao, Math and Economics. Scott Lowe, Engineering Physics. Dana Mohammed Zadeh, International and Area Studies. Andy Morris, an MBA candidate with Industrial Engineering as an undergrad. Mimi Nguyen, Finance and MIS. Ryan O'Melia, Zoology. William Pruitt, Finance. John Reed, College of Law. Chase Roberts, Finance and Entrepreneurship. And finally, Jeffrey Stewart, Chemical Engineering. Please join me in congratulating these young minds. Thank you so much. Now, what you don't see is a lot of the behind-the-scenes things that occur, and we have a great staff, some of which you met tonight, some of which you didn't get to hear from. But I do want to thank Colin Fitzsimons, Joel Martin, Cameron McCoy, Dr. Elaine Ham, of course Poseidon and Athena, Michael Harrison, and Chris Schilling, and of course Kim Saylor. So there are just so many people that go into tonight, and I think we owe them all a round of applause. Thank you. And, of course, one of my favorite parts is the lovely reception that we have to follow. So please join us for a few moments. Get to know these interns. I'm sure they'll be very aggressive and introduce themselves to you. And, again, thank you for spending your evening with us here at CCW. Good night.